Right now, as you watch this, there could be entire worlds brushing against ours, realms folded into the fabric of space, so tiny, so bizarre, that we'd never notice them. Think about that for a second. The universe isn't just vast, it might be layered like pages in a book we can't yet read. And here's the wild part, scientists aren't just guessing. They've got theories, real, mind-bending math, that suggests there could be not just the 3 dimensions we know, but maybe 10, 11, or even more, all hidden in plain sight. Today, we're diving into 30 of the most incredible ideas about these secret dimensions, from cosmic brains colliding to create universes, to holographic realities where everything you see is just a shadow of a deeper truth. This isn't sci-fi, this is the cutting edge of physics served up without the jargon. So buckle up, we're about to stretch your imagination way beyond length, width, and height. And trust me, by the end, you'll never look at the universe the same way again. Now, let's unravel the first mind-bending idea, string theory's vision of the cosmos. Picture this, the universe isn't just made of point-like particles, but tiny, vibrating strings. And here's the twist, for the math behind these strings to work, they need room to dance. Not just the 3 dimensions we know, but a total of 10, 9 of space and 1 of time. That's 6 extra dimensions curled up so tightly, they're invisible to us, like the grooves on a vinyl record too fine for the naked eye to see. These hidden dimensions aren't just random folds, they're shaped into intricate geometric forms called Kaluza-Klein manifolds. Imagine a garden hose from far away. It looks like a simple line, but up close, it's a cylinder. Similarly, these extra dimensions could be compactified, wound into shapes so tiny that even our most powerful microscopes can't spot them. Yet, their structure might explain why particles have different masses and forces. And here's where it gets wild. The way these strings vibrate in higher dimensions could determine everything from the weight of an electron to the strength of gravity. Think of it like musical notes on a guitar string. Each vibration pattern creates a different particle. So, the universe might literally be singing in dimensions we can't see. Now, if that doesn't make you question reality, just wait, because this is only the first stop on our journey through the cosmos' hidden layers. But what if our universe isn't just floating in empty space? What if it's more like a slice of bread in a cosmic loaf? That's the wild idea behind the Brane World Scenario. Picture our entire 3-dimensional universe as a membrane, or brane for short, drifting through a higher dimensional space called the bulk. And here's the kicker, there could be other brains out there, each with their own universes, just inches away in dimensions we can't perceive. Now, why does gravity feel so weak compared to other forces? Imagine you're on a trampoline, your weight bends the surface, but some of that pull leaks into the air around it. In the same way, gravity might be stretching into extra dimensions, diluting its strength in our brain. That's why it's so much feebler than electromagnetism or the nuclear forces. It's not confined to our slice of reality. And here's where things get explosive. Some theories suggest the Big Bang itself could have been a cosmic collision, 2 brains smashing together like cymbals, unleashing enough energy to birth an entire universe. If that's true, our cosmos might just be one ripple in an endless sea of crashing membranes. So next time you look up at the night sky, remember, we might be living on a floating sheet in a hidden cosmic ocean with untold worlds just beyond our grasp. And if that doesn't stretch your imagination, just wait, we're only getting started. Now, let's rewind the cosmic clock to the early 20th century, where 2 brilliant minds dared to imagine a universe with an extra dimension. Meet Theodore Kaluza and Oscar Klein, the pioneers behind a theory so elegant it could have rewritten physics. If only the universe had cooperated, their idea. A 5th dimension, curled up so tightly it's invisible to us, like a garden hose seen from a distance. Here's the genius part. Kaluza realized that if you add this tiny, hidden dimension to Einstein's equations of gravity, something magical happens. Electromagnetism, the force behind light and electricity, emerges naturally as if gravity and electromagnetism were two sides of the same cosmic coin. It was the first serious attempt to unify the forces of nature, and it all hinged on a dimension smaller than an atom. Klein took it further, suggesting that particles like electrons might just be vibrations in this compactified fifth dimension. Think of a guitar string, pluck it differently, and you get different notes. In the same way, particles could be notes played on the tiny, coiled strings of higher dimensional space. But why can't we see this extra dimension? Imagine an ant walking on a telephone wire. From far away, the wire looks one-dimensional, but up close, the ant knows there's a whole circular dimension wrapped around it. Our universe might be like that ant, oblivious to the microscopic loops hiding in plain sight. So while Kaluza-Klein theory didn't quite crack the code of unification, it planted the seeds for modern string theory and showed us that hidden dimensions aren't just science fiction, they might be the universe's best-kept secret. And speaking of secrets, wait until you hear how some theories suggest dimensions could be warped like cosmic funnels, but that's a story for another moment. Now, let's take a leap into one of the most mind-bending ideas in modern physics, the holographic principle. Picture this. What if everything you see, touch, and experience in our three-dimensional world is actually a projection from a two-dimensional surface, like a cosmic movie screen? It sounds like science fiction, but some of the brightest minds in physics are seriously considering it. The idea first gained traction when scientists studying black holes stumbled upon a paradox. According to quantum mechanics, information can never be destroyed, but black holes seem to swallow it whole. The solution: maybe the information isn't lost, it's just encoded on the black hole's event horizon, the point of no return. Think of it like a DVD storing a 3D movie on its flat surface. The event horizon could be storing all the information about what falls inside, projecting it back out in a way we don't yet fully understand. This led to the wild notion that our entire universe might work the same way. The AD/CFT correspondence, a groundbreaking concept in theoretical physics, suggests that a higher dimensional space like our universe could be mathematically equivalent to a lower dimensional boundary. In simpler terms, everything happening in our 3D world might just be shadows cast by processes happening on a distant 2D surface. Imagine standing in front of a hologram. From one angle, it looks flat, but tilt your head and suddenly it has depth. The holographic principle proposes that reality itself might be like that, an illusion of depth created by information stored on a flat surface at the edge of the cosmos. If this is true, it would mean that space, time, and even gravity aren't fundamental, they're emergent phenomena, like the ripples on the surface of a pond. It's a radical shift in how we think about reality, and it could be the key to unifying quantum mechanics and gravity. So next time you look at the night sky, ask yourself, are we living in a 3D universe, or are we just part of an enormous cosmic hologram? The answer might be stranger than we ever imagined. Now, let's push the boundaries even further with M-theory, the bold successor to string theory that demands not 10, but 11 dimensions to make sense of the universe. If string theory was already stretching our imaginations, M-theory snaps them like a rubber band. At its core, M-theory introduces the idea of membranes, specifically M2 and M5 branes floating in this 11-dimensional space. Think of these branes as cosmic sheets or bubbles, with our entire universe possibly existing on one of them. An M2 brane is like a two-dimensional sheet vibrating through higher dimensions, while an M5 brane is its five-dimensional cousin, a kind of sprawling cosmic landscape where the rules of physics might play out differently. What makes M-theory so fascinating is the sheer scope of possibilities it opens up. Instead of a single universe, it suggests a vast landscape of potential universes, each with its own unique set of physical laws. Some might have stronger gravity, others might have extra dimensions unfurled like ribbons. and a few could even be right next to ours, separated by a dimension we can't perceive. Visualizing 11 dimensions is no easy feat, but imagine higher dimensional shapes folding and twisting in ways that defy our everyday experience. A Kaluza-Klein manifold, a 6-dimensional shape string theorists love, might just be one piece of a much larger, more intricate puzzle in M-theory. This theory doesn't just add another dimension to the mix, it weaves them together into a framework where strings, branes, and even entire universes interact in ways we're only beginning to grasp. Could our reality be just one membrane in a sea of countless others? If M-theory is right, the answer might be hiding in those elusive 11 dimensions. Now, let's zoom in on something truly mind-bending: the idea that hidden dimensions might not be tiny at all, but as large as a millimeter in scale. That's right, while most theories tuck extra dimensions away at unfathomably small sizes, some models suggest they could be hiding in plain sight, just beyond our everyday perception. This theory of large extra dimensions flips the script on how we think about quantum gravity. Instead of cramming extra dimensions into the subatomic realm, they could stretch out just enough to influence gravity in ways we haven't noticed yet. Imagine gravity as a force that's not confined to our 3 dimensions. It could be leaking into these larger hidden spaces, which might explain why it's so weak compared to other fundamental forces. Scientists are actually testing this wild idea with tabletop experiments, searching for tiny deviations in Newton's laws of gravity at microscopic distances. If gravity behaves differently when you measure it between objects separated by less than a millimeter, it could be a smoking gun for these hidden dimensions. Picture a split-screen visual: on one side, the familiar world where gravity works as expected, and on the other, a microscopic realm where the rules start to bend. What's fascinating is that if these large extra dimensions exist, they wouldn't just rewrite physics textbooks, they'd open a doorway to understanding why the universe works the way it does. Could gravity's mysterious weakness be because it's diluted across dimensions we can't see? The answer might be closer than we think, lurking in the space between a grain of sand and the tip of a pin. Now, let's take a step into the warped side of hidden dimensions, where space itself isn't just extra, but twisted. The Randall-Sundrum model throws a curveball at our understanding by proposing that a 5th dimension isn't just out there, it's warped, like a funnel bending the fabric of reality. Here's the puzzle it solves. Why is gravity so incredibly weak compared to the other forces? Imagine gravity as a whisper that gets lost in a maze. In this model, our universe sits on one end of a warped 5th dimension, while gravity's source, the real heavyweight, is anchored far away on the other end. The warping acts like a cosmic amplifier, diluting gravity's strength as it travels across this curved space to reach us. It's not that gravity is weak, it's just stretched thin by the geometry of higher dimensions. Picture this funnel-like dimension, visually a steep slope where gravity weakens as it climbs toward our brain, like a signal fading over a vast distance. This elegant twist doesn't just explain gravity's feebleness, it sidesteps the need for undiscovered particles or untested physics. The hierarchy problem, the huge gap between gravity's strength and other forces, might just be an illusion created by the hidden contours of space. What's thrilling is that this warped dimension isn't some abstract math trick. It could leave fingerprints in particle collisions or gravitational waves, hints that we're living on a cosmic hillside with reality tilted just out of view. The next time you drop a pen, remember, gravity's weakness might be the echo of a dimension bent beyond our sight. But what if hidden dimensions aren't just warped? What if they breathe? Let's unravel the mesmerizing idea of cyclic dimensions, where the fabric of space itself pulses like a cosmic heartbeat. Imagine a universe where dimensions don't just exist, they expand, contract, and reset in an endless loop, shaping the very epochs of reality. This theory ties into conformal cyclic cosmology, a bold reimagining of time and space proposed by Nobel laureate Roger Penrose. Here's the wild part. Instead of a one-way trip from Big Bang to heat death, the universe might undergo infinite cycles. Each cycle begins with dimensions stretched thin, then collapses into a dense, smooth state only to rebound into a new expansion phase. Picture it like a cosmic accordion, with dimensions squeezing and stretching across aeons. What's even more mind-bending is how this could erase the boundaries between cycles. At the end of each epoch, black holes might evaporate into pure energy, and space-time itself could become featureless, no stars, no galaxies, just a blank slate. Then, as dimensions contract and reboot, quantum fluctuations spark a new Big Bang, birthing a fresh universe with slightly tweaked physics. It's not science fiction, it's a mathematical possibility where dimensions themselves hold the memory of past cycles. The beauty of this idea: it could explain mysteries like the low entropy of our early universe or the eerie uniformity of the cosmic microwave background. If dimensions cyclically reset, they might carry faint imprints from previous iterations like echoes of a forgotten age. Visualize space as a looping film reel, where each frame is a new cosmic dawn, and the projector is the hidden rhythm of collapsing and expanding dimensions. So next time you gaze at the night sky, consider this: the dimensions around us might not be static. They could be alive, pulsing in a grand, eternal dance, one that's been repeating long before us and will continue long after. Now let's zoom way into a world where space itself isn't smooth or whole, but fractured and infinitely intricate. Imagine space-time at the tiniest scales, not as a neat grid, but as a swirling, self-repeating pattern, like a cosmic fingerprint that never quite settles. This is the realm of fractal dimensions, where the fabric of reality might not play by the rules of whole numbers. At the quantum level, space-time could resemble a fractal, a shape that repeats itself no matter how closely you look, like a never-ending set of Russian dolls. Think of the famous Mandelbrot set, where every twist and turn reveals new layers of complexity. Here, the Hausdorff dimension comes into play, a mathematical way to measure these in-between spaces. Unlike our familiar 3 dimensions, fractal dimensions could be fractional, say 2.5, meaning space-time at this scale isn't fully filled or entirely empty, but something eerily in between. This ties into the mind-bending concept of quantum foam, the idea that at unimaginably small scales, space-time bubbles and churns like a frothy sea. Particles pop in and out of existence, and the very geometry of space fluctuates wildly. Some theories suggest these fluctuations could create fractal-like structures, where dimensions blend and blur. Picture walking through a forest where every step takes you deeper into a maze of branches that look the same no matter how far you go. That's the haunting beauty of fractal spacetime. Why does this matter? Fractal dimensions could solve puzzles like the singularity inside black holes or the bizarre behavior of particles at quantum scales. If spacetime isn't smooth but instead a tangled fractal web, it might explain why gravity and quantum mechanics clash. They're operating on different dimensional blueprints. Visualize the universe as a vast, shimmering fractal, where every layer holds secrets about the next, and the act of observing it changes its very nature. So the next time you see a snowflake or a fern leaf, remember, the cosmos might be echoing those patterns in the hidden architecture of reality itself. Now let's shift gears to a theory that brings symmetry into the spotlight, literally. Supersymmetry, or SUSY for short, isn't just a fancy idea. It's a potential game changer for how we understand the universe's hidden dimensions. Picture this: every particle we know, electrons, quarks, photons, might have a hidden twin, a superpartner lurking in higher dimensional space. These sparticles could be the missing puzzle pieces that explain why extra dimensions stay neatly compactified instead of unraveling into chaos. Here's how it works. In our everyday 3-dimensional world, particles like electrons are fermions, while force carriers like photons are bosons. Supersymmetry proposes a cosmic balancing act where every fermion has a bosonic partner and vice versa. For example, an electron superpartner would be the selectron, a boson with similar properties but different spin. These particles could exist in higher dimensions, interacting with our familiar particles in ways we're only beginning to model. Why does this matter for hidden dimensions? Think of compactified dimensions like a tightly wound spring. Without something to stabilize them, they'd either snap open or collapse entirely. Sussy particles could act as cosmic glue, their interactions in higher dimensional space providing the tension needed to keep extra dimensions neatly folded. It's like having invisible scaffolding holding up the hidden architecture of reality. Particle colliders like the Large Hadron Collider are hunting for signs of these particles. If they exist, their discovery would not only confirm supersymmetry, but also give us indirect evidence of higher dimensions. Visualize a particle collision where familiar tracks suddenly reveal anomalous, ghostly traces of particles briefly bridging our world with unseen dimensions. So while supersymmetry remains unproven, its elegance lies in how neatly it ties together multiple mysteries: dark matter, the hierarchy problem, and now the stability of hidden dimensions. If Sussy is real, we're not just mapping particles, we're uncovering the silent partners that shape the very fabric of the cosmos. But what if time isn't just the fourth dimension we've always assumed it to be? Let's take a step into a mind-bending idea. Time might actually be a higher dimension, one that operates beyond our usual understanding. This isn't just science fiction, it's a serious theory that reshapes how we see reality. Imagine the universe as a frozen block where past, present, and future all exist simultaneously. This is the block universe theory, where time isn't a flowing river but more like a loaf of bread, every slice from the first to the last already baked and sitting there. In this view, what we experience as the passage of time might just be our limited way of perceiving a much larger, unchanging structure. Now, here's where it gets wild. If time is a higher dimension, it could mean that what we call now is just one point in a vast, multidimensional tapestry. Think of a tesseract, a four-dimensional cube, where time isn't linear but folded, twisted, or even looping back on itself. Animations of tesseracts show how a higher dimensional being might see time as a shape, not a straight line. They could, in theory, move freely between moments like we flip through pages in a book. This idea also challenges our notion of cause and effect. If time is fluid in higher dimensions, events might not be as fixed as they seem. Some theories suggest that quantum particles remember their future states, hinting at a reality where time's arrow isn't one-directional. So why does this matter? If time is a higher dimension, it could unlock answers to some of physics' biggest puzzles, like why quantum mechanics and relativity don't quite mesh, or how black holes warp reality. It forces us to ask, are we just seeing a shadow of a much deeper cosmic structure? The next time you check your watch, remember you might not just be tracking seconds. You could be glimpsing the edge of a dimension we're only beginning to imagine. Now, let's venture into the shadows of the cosmos, where the mysteries of dark matter and dark energy might be hiding in plain sight, just beyond our dimensional reach. Picture this: what if the reason we can't directly detect dark matter isn't because it's invisible, but because it exists in parallel dimensions, subtly influencing our universe from the outside? This idea isn't just wild speculation, it's rooted in serious physics. Brane World models suggest our universe could be a three-dimensional brane, floating in a higher dimensional space, with dark matter particles lurking in these extra dimensions. They'd interact with our world almost exclusively through gravity, which could explain why dark matter seems to ghost through everything without leaving a trace. Think of it like a neighbor's radio playing faintly through the walls. You can't see the source, but you know it's there. Here's where it gets even stranger. Dark energy, the force accelerating the universe's expansion, might also be leaking into our brain from these hidden dimensions. Some theories propose that what we perceive as dark energy could actually be the gravitational push of another universe just out of reach, warping our space-time from beyond. To visualize this, imagine our universe as a sheet of paper with visible matter as ink on its surface. Dark matter, then, would be ink on another sheet, hovering close enough to bend our paper with its gravity, but never quite touching. This contrast between the seen and unseen could rewrite our understanding of cosmic structure, from galaxy formation to the fate of the universe itself. So why does this matter? If dark dimensions are real, they'd bridge the gap between quantum mechanics and gravity, solving one of physics' biggest headaches. Plus, it means the cosmos might be far more crowded and far weirder than we ever imagined. The next time you look up at the night sky, remember, the darkness isn't empty. It might just be hiding dimensions we're only beginning to sense. But what if the strangest cosmic connections aren't just happening around us, but through dimensions we can't even see? Take quantum entanglement, that bizarre phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. It's as if they're whispering secrets across the universe faster than light should allow. But here's the twist: what if they're not actually communicating at all? Some physicists propose that entangled particles might be linked through hidden higher dimensions, like threads passing through the fabric of reality itself. This idea, known as the ER=EPR conjecture, suggests that entanglement could literally be a microscopic wormhole, a tunnel through space-time connecting the particles. Picture 2 points on a sheet of paper. In our three-dimensional world, the shortest path between them is a straight line, but fold the paper and suddenly those points touch. Higher dimensions could work the same way, creating shortcuts that make spooky action seem perfectly natural. Imagine 2 dice rolling in separate rooms, always landing on matching numbers. In our universe, that's impossible without some hidden connection. But if those dice were linked through an extra dimension, like rooms connected by a secret passage, their synchronized behavior suddenly makes sense. That's the eerie elegance of this theory. It turns quantum weirdness into geometry, and here's where it gets wilder. If entanglement really is a dimensional bridge, it could mean that the fabric of space-time is stitched together by countless invisible threads, weaving particles into a cosmic web far more intricate than we ever imagined. It might even hint at how gravity and quantum mechanics could finally shake hands through the hidden architecture of the universe itself. So next time you hear about entangled particles defying logic, remember, the answer might not be in the space we see, but in the dimensions we're only beginning to uncover. The universe's greatest magic tricks could all be happening just out of view. Now, let's unravel another cosmic mystery hiding in plain sight: cosmic strings, the universe's ancient scars. Picture the early cosmos as a bubbling cauldron of energy, cooling and settling into the universe we know today. But just like cracks forming in ice as it freezes, the fabric of space-time might have developed flaws during this cosmic transition. These flaws could be cosmic strings, infinitely thin, unimaginably dense threads stretching across the universe, remnants of higher dimensions left over from creation. Think of them as cosmic guitar strings vibrating with the energy of the Big Bang itself. Unlike black holes or stars, these strings wouldn't be made of matter but pure space-time curvature, warping everything around them. If one passed through your room, you wouldn't see it, but you might notice your reflection splitting in two as light bends around its immense gravitational pull. Here's where it gets mind-bending. Some theories suggest these strings could be topological defects, wrinkles in higher dimensional space that got trapped when our universe snapped into its current form. Imagine smoothing out a crumpled sheet of paper. Some folds might stubbornly resist, leaving permanent creases. Cosmic strings could be those creases, but instead of paper, they're kinks in the very structure of reality. And their effects anything but subtle. A single cosmic string could warp spacetime so severely that it creates time loops or even double images of distant galaxies. If two strings crossed, they might spark cataclysmic bursts of energy or spawn new universes entirely. While we haven't spotted one yet, their gravitational fingerprints could be hiding in the cosmic microwave background, waiting to be decoded. So the next time you gaze at the night sky, remember, the universe might be threaded with invisible cosmic strings, silent witnesses to the higher dimensional drama that shaped everything we know. And who knows, one day we might just tug on those threads and unravel the universe's deepest secrets. Now, let's take a playful leap into the realm of science fiction, but with a twist of real mathematical possibility. Imagine beings that don't just live in higher dimensions but can perceive and even manipulate them. Think of it like the classic flatland thought experiment, where two-dimensional creatures struggle to comprehend our three-dimensional world. But what if we're the ones who are limited, unable to grasp the full reality of 4, 5, or even more dimensions? These dimensionally transcendent beings wouldn't just see more, they'd experience reality in ways we can't even visualize. To them, our three-dimensional world might look as flat and confined as a sheet of paper. They could move through walls, reach inside objects without opening them, or even observe our entire timeline at once, like flipping through the pages of a book. Here's where the math gets fascinating. Higher dimensional geometry suggests that objects in 4 or more dimensions would cast shadows in our three-dimensional space, distorted, fragmented glimpses of their true form. A 4-dimensional cube or tesseract, for example, would appear to us as a shifting, impossible shape, morphing in ways that defy our intuition. And while this sounds like pure sci-fi, some physicists argue that if higher dimensions exist, it's not unreasonable to imagine life evolving there. The rules of chemistry and biology might be different, but the underlying principles could still apply. After all, if the universe can build us in 3 dimensions, why not something even more complex in 4 or 5? So the next time you feel like you've got a handle on reality, remember, there might be beings out there laughing at our 3-dimensional struggles, watching us fumble through a world they see as child's play. And who knows, maybe one day we'll catch a glimpse of their shadows and realize just how small our corner of the cosmos really is. Now, let's shift gears to a theory that turns cosmic creation into something like a high-stakes bumper car ride. Picture this, our universe isn't just floating alone in higher dimensional space, it's one of many membranes or branes crashing into each other in a cosmic dance. This is the colliding brane multiverse, a wild twist on how universes might be born. According to the ekpyrotic model, the Big Bang wasn't a singular explosion from nothing. It was the aftermath of 2 branes smashing together in a higher dimensional realm. Think of it like 2 sheets of paper slamming into each other in a windstorm, except these sheets are entire universes. The energy from that collision would have been so intense, it could have sparked everything we see today: galaxies, stars, even the fabric of spacetime itself. Here's where it gets even more mind-bending. Unlike the traditional inflationary theory, which says the universe expanded rapidly from a tiny point, the ekpyrotic model suggests our cosmos was born from a clash of titanic structures. Inflation explains the universe's smoothness with a burst of exponential growth, but the brane collision idea offers an alternative. Maybe the universe was stretched and smoothed by the sheer force of that impact. And if this sounds like a one-time event, think again. In this model, branes could keep colliding over and over, creating endless cycles of universes. One crash might birth our cosmos, while another collision in some distant higher dimensional space could spawn a whole new reality with entirely different laws of physics. So the next time you look up at the night sky, remember, our universe might just be the aftermath of a cosmic fender bender, one of countless others in an endless multiverse of colliding membranes. Who knows what other universes are out there, born from collisions we can't even see? But what if black holes aren't just cosmic vacuum cleaners sucking everything in? What if they're actually gateways to other dimensions? Let's take a dive into one of the most mind-bending ideas out there, dimension-shifting black holes. Imagine a black hole's singularity, that point of infinite density at its core, not as a dead end but as a tunnel. Some theories suggest that instead of crushing matter into oblivion, singularities might punch through the fabric of space-time, sending whatever falls into another dimension entirely. It's like a cosmic subway system where black holes are the stations and the tunnels lead to who knows where. This idea ties into something called white holes, theoretical opposites of black holes. While black holes pull everything in, white holes would spew matter and energy out. If a black hole connects to a white hole through a higher dimensional bridge, it could mean that what gets swallowed here might reappear somewhere else in the universe, or even in another universe altogether. And here's where Hawking radiation comes into play. Stephen Hawking showed that black holes aren't completely black, they slowly leak energy over time. Some physicists speculate that this radiation might carry traces of whatever slipped into the black hole, scrambled but not entirely lost. If that's true, then black holes could be cosmic recyclers, transforming matter into something new before ejecting it back out, possibly into another dimension. Picture this, a star getting too close to a black hole, stretching like taffy as it's pulled in. But instead of vanishing forever, its particles might get threaded through higher dimensional space, emerging somewhere completely different. It's a wild thought, one that blurs the line between destruction and transformation. So the next time you hear about a black hole, don't just think of it as a one-way trip to nowhere. It might just be the universe's most extreme interdimensional shortcut. Who knows what or where lies on the other side? Now, let's tune into something truly unexpected, the idea that hidden dimensions might actually sing. That's right, we're talking about compactified dimension music, where the tiny, curled-up dimensions predicted by string theory could vibrate like the strings of a cosmic instrument. Think of it this way, if these extra dimensions are as small as string theory suggests, they wouldn't just sit there silently. They'd hum, resonate, and even harmonize. Just like plucking a guitar string produces different notes depending on how it vibrates, the way these compact dimensions oscillate could determine the properties of fundamental particles. A higher-pitched vibration might give us an electron, while a deeper tone could manifest as a quark. It's as if the universe has its own hidden symphony, with every particle playing its own unique note. This isn't just poetic speculation, it ties directly into string harmonics. In string theory, particles aren't tiny dots but vibrating strings, and their music defines their mass, charge, and behavior. The harmonics of these strings could be influenced by how the extra dimensions vibrate around them. Some physicists even suggest that if we could listen closely enough to the quantum realm, we might detect a mathematical melody underlying reality itself. Here's where it gets even wilder. What if the constants of nature, like the speed of light or the strength of gravity, are just the universe's way of staying in tune? If the dimensions vibrate at certain frequencies, those vibrations could lock in the rules of physics as we know them. Change the pitch and you might change the laws of the cosmos. So next time you hear a beautiful piece of music, remember, the universe might be playing its own composition with hidden dimensions as the orchestra. Who knows, maybe one day we'll decode the soundtrack of reality itself. But what if consciousness itself is tapping into these hidden dimensions? This brings us to a mind-bending idea: dimensional consciousness. Imagine your thoughts, your awareness, even your sense of self might not be confined to the three-dimensional world you perceive. Some theories, like the Penrose-Hameroff Orch or model, suggest that consciousness could arise from quantum processes deep inside your brain's neurons, processes that might extend into higher dimensions. Think of it like this: if the brain is a receiver, could it be picking up signals from dimensions beyond our usual perception? Materialist views argue consciousness is purely a product of the brain's physical structure, nothing more. But panpsychists take it further. They propose that consciousness might be a fundamental feature of the universe, woven into the fabric of reality itself, possibly even interacting with those extra dimensions string theory describes. Here's where it gets even stranger. If higher dimensions influence our consciousness, could that explain phenomena like intuition, déjà vu, or even near-death experiences? Some speculate that these moments might be glimpses into a reality where more dimensions exist, where the brain briefly taps into a deeper layer of existence. Of course, this is still speculative, but it opens up wild possibilities. Could advanced civilizations manipulate higher dimensions to enhance their minds? Could meditation or altered states of consciousness be ways to tune in to these hidden layers? The idea blurs the line between science and philosophy, challenging us to rethink not just the universe but our place within it. So the next time you pause to reflect on your own thoughts, consider this. Your mind might be touching realms far beyond what your eyes can see. Now, let's shift gears to something equally fascinating: quantum gravity's take on hidden dimensions. While string theory and brains dominate the conversation, there's another compelling idea. What if dimensions aren't smooth and continuous but instead built from tiny, discrete pieces? That's where loop quantum gravity and causal sets come into play. These theories suggest spacetime might be woven together like a fabric made of microscopic atoms, with dimensions emerging from their interactions. Picture this: instead of a seamless, infinite universe, imagine spacetime as a pixelated grid, where each pixel represents the smallest possible unit of space and time. In loop quantum gravity, these pixels form loops that intertwine to create the fabric of reality, while causal sets propose a more abstract network of events linked by cause and effect. Both ideas hint that dimensions could be more like a mosaic, constructed from fundamental building blocks rather than existing as a smooth backdrop. This changes everything. If dimensions are emergent, not fundamental, it could solve one of physics' biggest headaches: uniting gravity with quantum mechanics. In this pixelated spacetime, gravity wouldn't be a force warping a smooth continuum, but a result of how these spacetime atoms connect and interact. Think of it like a digital image. Up close, you see individual pixels, but step back and the picture becomes fluid. The implications are staggering. If spacetime has a smallest possible scale, it could prevent the infinities that plague black hole singularities or the Big Bang. It might even explain why we perceive only 3 spatial dimensions. The others could be hidden in the way these atoms stitch together. So, next time you gaze at the night sky, remember, the universe might not just be vast, it could be pixelated, with dimensions glued together by the quantum code of reality itself. Now, let's take a step into the extreme where the very fabric of reality starts to unravel. Imagine pushing the universe to its limits, cranking up the energy to unimaginable levels near the Planck scale. What happens to dimensions then? Some theories suggest they don't just hide, they vanish. At these extreme energies, spacetime itself might undergo a radical transformation. Instead of the familiar 3 dimensions of space and 1 of time, the universe could effectively reduce to just 2 dimensions. It's as if the higher dimensions melt away, leaving behind a simpler, flatter reality. This idea isn't just wild speculation, it's rooted in frameworks like Horover-Lifshitz gravity, which proposes that at high energies, spacetime behaves differently, breaking the symmetry we're used to. Think of it like ice turning to water under heat. At everyday temperatures, ice holds its rigid structure, but crank up the heat and it liquefies. Similarly, dimensions might lose their structure under extreme conditions, collapsing into a lower dimensional state. This could explain why we don't perceive extra dimensions. They only manifest when the energy is low enough for them to freeze back into existence. The implications are mind-bending. If dimensions vanish at high energies, it could reshape our understanding of the early universe, where temperatures and energies were off the charts. Maybe the Big Bang wasn't just an explosion of matter, but a dimensional phase transition, a moment when the universe's very structure snapped into place. So, next time you think about the universe's building blocks, remember, dimensions might not be fixed. They could flicker in and out of existence depending on how hot and chaotic things get. And that's a reminder reality is far stranger than we often assume. Now, let's shift our gaze to the cosmic horizon, where the universe's expansion holds a tantalizing secret. What if dark energy, the mysterious force accelerating the universe, isn't just lurking in the shadows of our dimensions, but is instead a ghostly echo from higher ones? Enter holographic dark energy, a theory that ties the universe's runaway expansion to the hidden dimensions we've been exploring. Here's the idea: in holographic models, our three-dimensional reality might be a projection from a two-dimensional boundary, like a cosmic movie screen. But this isn't just about space, it's about energy. Vacuum fluctuations, those tiny quantum jitters in empty space, could be influenced by higher dimensions, creating a pressure that drives the universe apart. Think of it like ripples on a pond. If the pond's surface is our universe, the ripples might be shaped by deeper, unseen currents, the extra dimensions beneath. This isn't just poetic imagery. The math suggests that holographic dark energy could explain why the universe's expansion is speeding up. Normally, dark energy is treated as a constant, but in this framework, it's dynamic, evolving as the universe grows. It's as if the holographic screen stretches and the projection, our reality, stretches with it. The implications are profound. If holographic dark energy is real, it means the fate of the cosmos is written in dimensions we can't see. Accelerated expansion isn't just a quirk of our universe, it's a signature of something deeper, a higher dimensional dance we're only glimpsing from the sidelines. So, the next time you hear about dark energy, remember, it might not be a property of our space, but a message from beyond it. And that's the beauty of these theories. They turn the universe's biggest mysteries into clues, pointing us toward dimensions just out of reach. Now, let's rewind the cosmic clock back to the universe's fiery infancy, where dimensions themselves might have been in flux. Picture the early cosmos not as the stable, four-dimensional stage we know today, but as a seething, higher-dimensional soup. Just as water freezes into ice, the universe could have undergone a dramatic phase transition, locking some dimensions into place while others curled up or vanished entirely. Here's how it might have worked. In the extreme heat of the Big Bang, all dimensions, perhaps 10 or 11 of them, were symmetric and unbroken, like a perfectly smooth pond. But as the universe cooled, that symmetry shattered. Some dimensions stretched out, becoming the vast space we move through, while others crumpled into scales so tiny we'd never notice them. It's like blowing up a balloon. The surface expands into a recognizable sphere, but the air inside the extra dimensions stay hidden, compressed. This isn't just speculation. Theories like string theory and brane cosmology suggest that dimensional phase transitions could explain why we perceive only 3 spatial dimensions. The math even hints at cosmic defects left behind. Think of cracks in ice that might manifest as cosmic strings or other exotic structures in today's universe. What's wild is that this process might not be unique. If other universes exist, they could have frozen into different dimensional configurations, some with more visible dimensions, some with fewer. Our three-dimensional reality might just be one possible outcome in a multiverse of geometric possibilities. So next time you marvel at the vastness of space, remember, it might be the relic of a cosmic deep freeze, a snapshot of dimensions caught mid-transformation. And who knows, somewhere out there, other universes could be unfolding in shapes beyond our wildest imagination. Now, let's stretch our imaginations beyond the familiar and ask a mind-bending question. What if life exists in dimensions beyond our own? Picture a universe where biology plays by entirely different rules, where the very geometry of space reshapes the building blocks of existence. In our three-dimensional world, life relies on chemistry with strict geometric constraints. Molecules fit together like puzzle pieces, enzymes dock with precision, and DNA twists in its iconic double helix. But in higher dimensions, these rules could unravel or rewrite themselves entirely. A four-dimensional cell, for example, might have structures we can't even visualize, membranes that fold in impossible ways, or metabolic pathways that branch through unseen directions. Some theories suggest that in higher dimensions, the forces governing life could behave differently. Electromagnetism might weaken or strengthen, altering how atoms bond. Gravity could play a more dominant role, leading to organisms with entirely new forms of locomotion or support. Imagine creatures that don't just move up, down, left, or right, but in directions we can't point to, navigating a world with extra axes of freedom. But here's the catch: could such life even interact with us? If higher dimensional beings exist, they might perceive our three-dimensional world as flat or fragmented, the way we'd see a two-dimensional shadow of a cube. They could be all around us, undetectable, their biology operating on a plane beyond our senses. This isn't just science fiction. Mathematicians and physicists have modeled how fundamental processes like replication or evolution might function in higher dimensions. Some simulations hint that complexity, and maybe even life, could thrive in these exotic landscapes. So while we've yet to find evidence of extra-dimensional life, the possibility invites us to rethink what biology could look like in the grand tapestry of the multiverse. After all, if life emerged here against cosmic odds, who's to say it hasn't blossomed elsewhere, in shapes and forms beyond our wildest dreams? Now, let's twist our understanding of time itself with a theory that bends the rules of cause and effect. Imagine a hidden dimension where time isn't just a straight line but a loop, a place where the future could reach back into the past, and events might circle back on themselves like a cosmic Ouroboros. This is the wild idea behind time like extra dimensions. In some models, compact higher dimensions could have an axis that behaves like time, creating pathways known as closed time-like curves. These aren't just sci-fi time loops, they're mathematically plausible structures where a particle, or even an entire universe, could return to its own past. Picture a twisted ribbon where every twist represents a moment folding back on itself, creating a feedback loop of cause and effect. But here's the puzzle: if time loops exist, why don't we see paradoxes everywhere? Why can't you go back and stop your parents from meeting? Physicists propose clever safeguards like the Novikov self-consistency principle, which suggests the universe would naturally prevent contradictions. Any attempt to change the past would simply reinforce what already happened, like a river flowing around a rock, always finding the path of least resistance. Some theories even suggest these time-like dimensions could explain quantum weirdness. Particles entangled across space might secretly be linked through higher dimensional time loops, their fates intertwined in ways we can't perceive. Visualize a tesseract, a 4D cube where timelines weave through each other like threads in a tapestry, hidden from our three-dimensional view. Of course, this raises dizzying questions. Could advanced civilizations harness these dimensions for time travel? Or are they nature's way of keeping causality intact, like invisible railguards on the tracks of reality? One thing's certain: time-like dimensions remind us that the universe's rulebook might still have pages we haven't even glimpsed yet. Now, let's step into a world where reality has a perfect twin, a hidden dimension that mirrors our own in every way. This is the mind-bending concept of mirror dimensions, where the universe might have a parallel space with identical physical laws but flipped properties, like a cosmic reflection. Imagine matter in our dimension having a mirrored counterpart, particles that look the same but behave slightly differently, like a left-handed version of a right-handed glove. These mirror dimensions could explain some of physics' biggest mysteries, like sterile neutrinos, ghostly particles that barely interact with normal matter. If they exist, they might be slipping in and out of mirror space, leaving only faint traces in our world. But here's where it gets even stranger. Some theories suggest dark matter, the invisible glue holding galaxies together, could actually be ordinary matter from this mirror dimension, leaking into ours through hidden connections. Picture a sheet of paper with two sides, our universe on one, its mirror twin on the other, with dark matter as shadows cast between them. Could there be entire mirror stars, planets, or even life just beyond our perception? While that's speculative, the math shows mirror dimensions aren't just fantasy. They're a serious possibility in models trying to unify physics. Think of it like a hidden layer of reality, perfectly synchronized with ours but forever just out of reach. So next time you look in a mirror, remember it might not just be reflecting light. It could be hinting at a whole other universe, flipped and folded into the fabric of spacetime itself. Now let's tune into a cosmic symphony where the very fabric of reality hums with hidden melodies. Picture the universe's dimensions not as silent, static structures, but as vibrating strings on a grand celestial instrument, each resonating at its own unique frequency. This is the mesmerizing idea of dimensional resonance, a theory proposing that the hidden dimensions we've been exploring might actually ring like tuning forks, shaping the fundamental constants of nature. Think of it this way: just as a guitar string's vibration determines its pitch, the resonant frequencies of these dimensions could define the universe's most basic properties, like the strength of gravity or the speed of light. Even the tiniest shift in these vibrations might alter reality as we know it. This concept ties back to physicist Paul Dirac's famous large numbers, mysterious cosmic ratios that seem too precise to be coincidence. Could these numerical harmonies be echoes of dimensions vibrating in perfect sync? Some models suggest these resonances might even explain why certain constants, like the fine structure constant, appear fine-tuned for life. Imagine dimensions pulsing in harmony, their oscillations locking into patterns that make stars, planets, and ultimately us possible. It's as if the universe is a finely calibrated instrument, with hidden dimensions providing the underlying rhythm. And here's the kicker: if we could detect these resonant frequencies, they might reveal clues about the shape and size of those extra dimensions. Experiments hunting for gravitational waves or quantum fluctuations could one day pick up the faint music of spacetime itself. So next time you hear a ringing bell, consider this: the entire cosmos might be singing along in dimensions we can't yet see. Now let's shift gears and consider something even more mind-bending. What if information itself exists in hidden dimensions? Imagine the universe not just as a physical construct, but as a vast, multidimensional library where every bit of data is stored in ways we can't yet perceive. This is the wild idea behind information dimensions, a theory suggesting that the very fabric of reality might be built on layers of data tucked away in higher dimensional space. Think of it like a hologram where a three-dimensional image is encoded on a flat, two-dimensional surface. In the same way, our three-dimensional world could be a projection of information stored in a higher dimensional framework. This ties into the it from bit concept, which proposes that everything in the universe, particles, forces, even consciousness, might emerge from fundamental bits of information. Quantum pioneer John von Neumann took this even further with his quantum logic theory, suggesting that the rules governing reality might operate like a cosmic computer processing data across multiple dimensions. Picture data structures floating in higher D space, their interactions shaping the laws of physics as we know them. And here's where it gets really intriguing. If information is stored in extra dimensions, it could explain mysteries like black holes preserving data despite swallowing matter, or quantum entanglement linking particles instantaneously across vast distances. The universe might not just be a place but a dynamic information processing system with hidden layers we're only beginning to decode. So next time you save a file on your computer, consider this: the cosmos might be doing the same thing, just in dimensions we can't yet access. Now let's step into a world where reality might not be what it seems. Picture this: what if the universe we see is just a shadow of something far more complex? This brings us to the eerie yet fascinating idea of dimensional shadows. Imagine living in a cave like in Plato's famous allegory, where all you've ever seen are shadows dancing on the wall, cast by objects you can't directly observe. Now apply that to our universe. What if the strange phenomena we detect, like the mysterious dark flow of galaxy clusters or odd patterns in the cosmic microwave background, are actually shadows of higher dimensional objects lurking just beyond our perception? Think of it like holding up a cardboard cutout under a light. The shadow it casts on the wall is a flattened, simplified version of the real object. In the same way, a four-dimensional shape passing through our three-dimensional space would leave behind a distorted imprint, something we might detect as an anomaly in the fabric of the cosmos. These shadows could explain why certain large-scale movements in the universe don't quite match our predictions, because we're only seeing a slice of the full picture. And here's where it gets even wilder. Some theories suggest that dark matter itself could be a shadow of higher dimensional gravity, leaking into our universe like faint echoes from a hidden dimension. It's as if we're detectives piecing together clues from a crime scene where the culprit exists in a world we can't see. So the next time you look up at the night sky, remember, what we perceive as the universe might just be the tip of an unimaginably vast multidimensional iceberg. The real question is, what's casting those shadows? Now let's push the boundaries of imagination one final time. What if dimensions themselves are nothing more than an illusion, a trick of perception emerging from something far more fundamental? This is the radical idea behind theories like the amplituhedron and twistor theory, which suggest that the very fabric of space and time might not be the ultimate reality. Instead, they propose that dimensions could arise from a deeper, dimensionless realm, like ripples on the surface of a pond. Picture this: the universe as we know it, with its three dimensions of space and one of time, could be a kind of projection, a shadow cast by mathematical structures that exist beyond dimensionality. The amplituhedron, for example, is a geometric object that simplifies particle interactions without relying on space or time at all. It's as if the messy, tangled threads of reality are woven into a pristine geometric shape, and what we perceive as dimensions are just folds in that shape. Twistor theory takes this even further, suggesting that spacetime itself is secondary, emerging from a more fundamental network of relationships. Imagine building a house out of Lego bricks. The house has walls, doors, and windows, but at its core, it's just a collection of simple, interlocking pieces. In the same way, our universe's dimensions might be built from something far simpler, something that doesn't even need the concept of here or there. So here's the mind-bending question. If dimensions are just an illusion, what does that say about reality itself? Are we living in a cosmic hall of mirrors where the rules we take for granted are just reflections of a deeper truth? The answer might lie in the pure geometric elegance of theories like these, where the universe collapses into something almost too beautiful to comprehend. And with that, we've reached the edge of our journey through the hidden dimensions of the cosmos. From vibrating strings to shadowy imprints, from colliding brains to dimensionless geometry, we've explored 30 theories that challenge everything we thought we knew about reality. Which one sparks your imagination the most? Let us know in the comments below. And don't forget to like, subscribe, and hit the notification bell so you never miss another dive into the universe's greatest mysteries. Until next time, keep looking beyond the visible. Who knows what dimensions we'll uncover together? As we wrap up this mind-expanding journey through the cosmos' hidden layers, let's take one last look at the sheer brilliance of these theories. From the tiny, curled-up dimensions of string theory to the holographic universe where our reality might just be a two-dimensional shadow, each idea stretches the limits of what we thought possible. Imagine gravity leaking from other dimensions, or entire parallel universes brushing against ours like soap bubbles in a higher dimensional foam. These aren't just wild guesses, they're serious attempts to solve physics' biggest puzzles, from dark matter to the nature of time itself. Think about it. What if the reason gravity feels so weak is because it's spreading into extra dimensions we can't see? Or if black holes are gateways to other dimensional realms? Even the fabric of space might be an illusion, emerging from something as elegant as a geometric shape beyond our perception. The deeper we dig, the more the universe feels like a cosmic puzzle waiting to be solved. So here's your challenge. Pick the theory that blows your mind the most. Is it the idea of vibrating strings shaping reality, or the possibility that we're living on a brain in a vast higher dimensional bulk? Maybe it's the holographic principle, suggesting everything you see is just a projection. Whatever it is, let's keep the conversation going. Drop your favorite in the comments and tell us why it captivates you. If exploring the unknown gets your brain buzzing, don't miss out on more adventures like this. Hit that like button, subscribe, and ring the notification bell so you're always first to dive into the next cosmic mystery. Until then, keep questioning, keep imagining, and remember, the universe is far stranger and more wonderful than we've ever dared to dream. See you in the next dimension.